Assalamu alaikum warahmatullahi ta'ala wabarakatuh. Bismillahirrahmanirrahim. Ladies and gentlemen, let's continue our tutorials about hourly analysis program. In this video, we're gonna complete our energy analysis tutorials. The previous video talked about how to add a chiller to the project library. So in this video, we're gonna talk about how to add the boiler and the cooling tower. Okay, let's start our project. Here we have the chillers. Okay, and now if you have any method to cool the water of the chiller, for example a cooling tower or any other method, open here. We'll find here the name of this cooling tower. So the modeling method is not always a cooling tower. Is not it does not mean that you always have a cooling tower. No, you may use dry cooler, just a dry cooler, or geo well or surface water as a method for cooling the chiller water. So here the cooling tower or dry cooler. For the chiller, dry cooler. Here are the dry coolers. Find here the dry cooler, here chilled water network and chilled water pump, and the dry cooler, and here the air cooled chiller. Okay, and here the cooling tower and the dry cooler. So here the cooling tower, or here dry cooler. Also you may use the JU water or well water or surface water just for cooling the water of the chiller. Okay, please, you have to know these cycles and read about them from any references. Okay, now here, so the cooling tower, dry cooler or JU well. Suppose that you wanna use the cooling tower as your method. So here is the configuration. So here, this is the name of the cooling tower water source and configuration, the water flow. Okay, here liter per second per kilowatt cooling for the chiller. You may use this as the water flow rate, but per 1 kilowatt of chiller cooling. Also, this is the liter per second. This is the total water flow rate of the cooling tower, but this is not easy as an initial designer. For the initial design, you may not know the total flow rate of the cooling tower. So it's recommended to use the difference here, and here are the minimum and maximum that are available. This is the delta T of the entering water of the cooling tower and the water that exits from the cooling tower. Okay. So for more information, click F1. So water flow rate. This item defines the fluid flow rate for heat rejection device. Flow can be specified in one of three ways. For GBM or liter per second, the flow is defined directly. For GBM per ton or liter per second per kilowatt, the program will calculate GBM automatically based on the cooling equipment capacity. This option should only be used for heat rejection equipment linked to a chiller plant, or WSHP or GWSHP or GSHP system. So when linking a JU well surface system to a changeover plant or a central heat pump plant, the GBM or delta T option should be used instead. So here delta T, the program will calculate GBM automatically based on the design heat rejection or heat extraction rate and the specified delta T. So water flow rate is used in simulation calculations. As you know, flow and heat rejection together determine the range of the heat rejection equipment, which is a key value that drives the performance of a cooling tower or dry cooler at design conditions. The design condition is the anchor point for calculation heat rejection equipment performance at off design and part load conditions. Okay, thanks. Now for the cooling tower model, so the design with bulb, what is the outdoor design with bulb? So click F1 to know. So design with bulb here defines the outdoor with bulb temperature for the full load design point for the cooling tower. Okay, and here the range at design. So the range at design defines the difference between the inlet and outlet water temperatures at the tower's full load design point. Please be careful. And the design approach defines the approach between the temperature of water leaving the tower and the outdoor with bulb temperature for the tower's full load design point. Okay? So after this, so together these first three inputs are used to define full load heat transfer effectiveness of the cooling tower. Once full load performance is known, performance at off design and part load conditions can be calculated using the thermodynamic algorithm. Gentlemen, you have to know the cycles of the refrigeration and the heat, and these kind of cycles will make you understand these inputs very quickly. This is the difference between you and any other technician or any other engineer who has no idea about the cycles. Okay, after this you have to input the full load fan kilowatt in I kilowatt per kilowatt or total kilowatt. Okay, here the full load fan kilowatt defines the fan motor input power at the tower's full load design point. This item can be entered in two ways, so as a motor input kilowatt or as the power ratio expressed in kilowatt per ton of heat rejection, kilowatt per kilowatt of heat rejection in metric units. To choose the units of measure for this input, use the drop down list to the right of the input item. Okay, for this. Okay, also the fan control, we have the type of control: fan cycling or water bypass or two-speed fan or variable speed fan. For fan cycling, what's the fan cycling here? So the fan control options are provided for maintaining water leaving the tower at the minimum set point for times of low wind bulb or low load. The four options listed in the drop-down list are the water bypass. Okay, let's start by fan cycling. Fan cycling, the tower fan will cycle on and off, thereby reducing the tower airflow and the heat transfer effectiveness to produce required return water temperature. Okay. Secondly, if you have water bypass, warm inlet water will be bypassed around the tower to blend with tower outlet water to produce the required temperature. So when using water bypass, the tower fan continues to run at full speed. Okay? And then two-speed fan. The two-speed fan, the tower fan uses a two-speed fan motor for conditions where higher flows are sufficient to maintain minimum set point. The fan will cycle between high and low speed. For conditions where lower flows are sufficient to maintain minimum set point, the fan will cycle between low speed and off. Okay, between low speed and off. The variable speed fan. So the tower fan uses a variable speed drive motor. Okay, drive, motor speed is adjusted to produce the airflow rate necessary to maintain the minimum set point temperature. Notice, gentlemen, if you use fan cycling, no other inputs, water bypass, okay. For two-speed fan, you have to input the fan electrical efficiency on percentage air flow at low speed fan or low fan speed, okay? So the fan electrical efficiency, this item is only required when the two-speed fan or variable speed fan control options are chosen. For two-speed fan control, specify the motor electrical efficiency. For variable speed fan, you have here variable speed fan. Okay, specify the overall electrical efficiency, which is a combined value accumulating for both the motor electrical efficiency and the VFD drive efficiency. Okay, for applications in the United States where the electrical efficiency is not known from tower selection data, it can be estimated from the minimum efficiency requirements dedicated by the Energy Policy Act of 1992. So you can collect here for other details. Also, if you use two-speed fan, you have to get the percentage airflow at low fan speed. It is 67 or 50%. Okay, the airflow here, this item is only required two-speed fan control is selected. Okay, specify the airflow at low fan speed as a percentage of the high-speed airflow. Typically, low fan speed is either 67% or 50% of high-speed airflow. So the dry cooler is used, okay, so the dry here, the design dry bulb temperature, okay, so near the dry cooler data, this program uses a thermodynamic algorithm to calculate the tower performance of the dry cooler's water to air heat exchanger for off design and part load conditions. Okay, so the design dry bulb defines the outdoor air dry bulb temperature for the full load design point of the dry cooler, and also the range at design is the same as the cooling tower here. Okay, and also the design approach. But the full load airflow, notice that here the full load airflow defines the airflow through the water to air heat exchanger in the dry cooler at the full load design conditions. Airflow can be defined in two ways. In terms of the airflow per unit heat rejection capacity, CFM per ton of heat rejection, or liter per second per kilowatt of heat rejection, or the second method as an airflow quantity CFM or liter per second. Units of measure, okay, you can draw it. When selection data of a specific dry cooler is being used, the airflow will typically be known and can be entered directly. When specifiers for the dry cooler are not known, it is usually more convenient to enter an airflow ratio, okay? So, together these first four inputs are used to define full load heat transfer effectiveness, as we said. And then the same things, gentlemen, as what we have done for the cooling tower, okay? For the JU well or surface water, here the same configuration, okay? But you have to fill or to get the average temperature of the water source, okay, per month. So click F1. So when geothermal well or surface water is used as the heat source or sink for HVAC equipment, average source water temperatures are defined for each month of the year. During energy simulations, the program assumes source water at this temperature is available for all equipment operating hours. That is entered in a table in which each row contains data for a different month. The left-hand column lists of the month name, and the right-hand column lists the average source water temperature for the month. So you can use this method, okay? And notice please, in HAP, generally you must know what is the minimum and what are the minimum and the maximum values, okay, to not get errors. So now you have this new cooling tower or the cooling method here for the project library. Now if you have a boiler for your project, you can add it. So here is the name of the boiler, and now you have to enter the fuel or energy type: natural gas, electric resistance, fuel oil, or propane. Then the boiler type: hot water or steam boiler. Then the boiler full load data. So the boiler capacity, you may make it auto size and the program will calculate it automatically, or you have to get the gross output for this. So you can click F1 also. So here the boiler capacity. This input defines whether the boiler capacity will be automatically calculated by the program or will be specified directly. For preliminary design or lead applications, where it is necessary to have the capacity automatically determined, place a check in the auto size box. When this boiler is later linked to a plant using the auto size capacities option, the program will automatically size the boiler based on peak plant load plus an oversizing factor specifying the plant inputs. For applications where the boiler capacity is known, leave the auto size box unchecked and specify the gross output of the boiler and its full load design condition. Note that the choice of auto size is important. If the auto size box is checked, then this boiler can only be linked to a plant which uses the auto size capacity option. Okay? If the auto size box is not checked, then the boiler can only be linked to a plant which uses the user-defined capacities option. Once a boiler is linked to a plant, this input should not be changed. Changing this value makes the boiler incompatible with its plant and will prevent you from running an energy simulation for the plant. And here the design hot water supply temperature, the temperature of the water that exits from the equipment, okay, and heat hot water flow rate can make in liter per second as a total, but you may get the delta T of it, okay. Also you can click F1. So the boiler hot water flow rate, this item defines the water flow rate for a hot water boiler at its design condition. This value is typically obtained from the boiler selection results or from catalog data. The flow can be defined in one of two ways, or GPM liter per second, or the delta. Okay, automatically calculate as what we said. So this flow rate is used in hot water distribution system calculations during the boiler plant simulation. This is in the calculation of full load pump input power for both constant speed and variable speed pumping applications. For constant speed, constant flow applications, it defines the flow rate for all boiler operating hours. For variable speed applications, it helps establish the minimum flow level of for the boiler. For example, if minimum flow is defined as 70%, minimum flow is calculated as 70% of the hot water flow rate you specify here. Okay. So when defining an auxiliary boiler for a WSHP loop, this flow rate is not used, and instead the flow rate defined for the cooling tower serving the WSHP system determines the loop flow. Also here for the overall efficiency, you have to get the overall efficiency. This input defines the overall efficiency for the boiler at the full load design condition. It is calculated as gross output divided by energy input. For combustion boilers, this efficiency accounts for combustion, flue and jacket losses in the boiler. For electric boilers, it accounts only for jacket losses. Okay. Also, if there are any boiler accessories, you have to get the input kilowatt. These items used for account electrical equipment such as combustion blower fans and fuel oil pumps that are sometimes used with combustion boilers. If the boiler is electric or is combustion but does not use these devices, enter a zero value. Okay. When the boiler is simulated, it's assumed the accessory electric equipment cycles with the boiler. For example, if accessory power of half kilowatt is specified and the boiler is operating at the part load ratio of 60%, the simulation will calculate a half kilowatt multiplied by 0.6 equal to 0.3 kilowatt for the accessory equipment power. After this, here the part load model. So you have here 1, 2, 3, 4 options. Constant efficiency. The constant efficiency, gentlemen, here this input specifies which method of modeling boiler of design and part load performance will be used in energy simulation calculations. For a hot water boiler, 4 options are offered. So the constant efficiency, this is a simplified model in which the overall efficiency specified for the boiler is used for all operating hours. Therefore, performance is not affected by part load ratio or hot water supply temperature. The user defined curve efficiency equal if PLR. Here we find part load performance percentage and the efficiency. So the user-defined curve efficiency, this is a simplified model in which the user defines a table of efficiencies at 10% steps of part load, okay? Not seen from 100 to 0. Of part load ratio to define boiler performance. Therefore, boiler performance is only considered as a function of a part load ratio. Other factors such as hot water supply temperature are not considered. For condensing boiler model efficiency, okay. Here with the option, this option HAP uses an energy plus curve fit performance model representing condensing boiler. This is a two-dimensional model in which performance is a function of both part load ratio and hot water supply temperature. Okay. Also, the non-condensing boiler model efficiency here. So with this option, HAB uses an energy plus curve fit performance model representing a non-condensing boiler. This is a two-dimensional model in which performance is a function of both part load ratio and hot water supply temperature. So for Energy Plus, you can check out the Energy Plus and their curves, and Energy Plus, one of the most important software programs that is used for energy analysis. So for a steam boiler, only the first two options above are offered. Notice, for constant efficiency and user defined. Okay, above the offer, the condensing and non-condensing models are specifically for hot water boilers and therefore are not relevant for steam applications. So now, gentlemen, after finishing all these data, click OK, and now we have here our bowl. So we have defined the chillers, cooling towers, boilers, and the next video we're gonna talk about how to use this equipment for the energy calculations and how to add them for your buildings and so on. Okay, thank you very much. Wassalamu alaikum warahmatullahi ta'ala wabarakatuh.